Alrighty, let's complete this activity together. So you had a chance to explore this on your own, and now we're going to talk about it. We're going to talk about each of these points and how they affect our least squared regression linear model. Okay, so let's start with point A. So I'm going to go to my applet. Looks about like this. So here is how my least squares regression line is looking now. And I'm going to approximate about where point A would be located, about there. Whoa, look at that. That changed the regression line a lot. What happened is, well, the regression line tilted quite a lot towards point A. And the y-intercept increased and the slope decreased. So for point A, we had this tilting that caused the slope to decrease, the y-intercept to increase. And then as for the correlation coefficient, well, that went down significantly from 0.9 to 0.4668. So the correlation decreased. So again, let's pretend this point was here. That's what our line sort of looked like. And then when I put point A, you can see this tilting. The line is tilting towards this particular outlier. Okay, let's now talk about point B. So point B is this point. Let's approximate it on the applet. So, and then watch what happens. So here's what my regression line is looking like right now. And I'm going to add in point B. Oh, and again, we can see the line is tilting towards this particular point. So what all exactly is happening? Well, the slope is decreasing. The y-intercept is increasing. And the correlation coefficient is decreasing. So let's write that in. So what did we see that happened? Well, the slope decreased. The y-intercept increased. And the correlation coefficient decreased. And so for points A and for points B, what we can kind of summarize for those 2 points is that those points actually tilt the line. Both A and B have this phenomena happening where the line is literally tilting towards it to meet it. Okay? Okay, now let's look at C and D. So point C is right here. Let's add that into this applet. Point C. Okay, that actually didn't change too much. I mean, the line is sort of shifting downwards, but it seems like the slope is staying about the same. We could probably say the y-intercept is decreasing, but the slope is staying about the same. Now, the correlation coefficient is changing. The correlation coefficient is decreasing. And that should make sense because that slope is, that particular point is out of pattern. But the slope stays the same. There's no tilting happening. The y-intercept does decrease because there's this shifting down that's happening. And the correlation coefficient does decrease because that point is out of pattern. And last point we're going to test is this point here, point D. So here we go. Let me put the regression line in. So point D is similar to point C, except instead of underneath the LSRL, it's above. Let's put it right there. Okay, again, similar kind of thing. We can see it's not tilting the line. It is shifting it up, and it is decreasing the correlation coefficient, but there's no tilting happening. So the slope is remaining relatively same. It does shift the line up, so we will see an increase in the y-intercept, and that point is out of pattern, so we should expect a decrease in the correlation coefficient. And so to summarize sort of points C and D here, we can say that these points shift. It shifts the line up or down. Okay? And notice, like, I'm going to sort of sketch in our mean X and Y lines really quickly. So notice the mean of the X's and the mean of the Y's about like there, okay? So this is our X bar and this is our Y bar. And notice, like, these points C and D, they are really close to X bar. So, and these points A and B are quite far away from X bar. So what we are going to come to learn, and this is a established math fact basically, is that outliers that are far away from X bar, we say those points have high leverage. So these points, A and B, will be considered high leverage points because they're far away from X bar. We're going to define that in a minute. But okay, really quickly, let's answer 3. Why are points A, B, C, and D considered outliers? Well, because basically they don't follow the overall linear trend. We can also think of this as they have large residuals. Which outliers have the greatest impact on the LSRL, vertical or horizontal? Well, as I just discussed, these sort of horizontal outliers that have these large residuals vertically away, but are still very close to X bar, those barely change our model at all. I mean, we definitely saw some correlation change and we saw slight shifting, but they weren't anywhere near as influential as A and B, these vertical outliers, okay? Excuse me, these horizontal outliers. This is the horizon. Horizontal outliers, okay? So the answer to this question is the horizontal ones. So the horizontal outliers. We also call those high leverage points. The other thing is for A and B, we would refer to those as influential points. Because those are points that, if removed, that substantially changes our model. Okay. So let's define a couple of things So wrap up your writing on this page for a moment, and then we're going to turn to page 15, top of page 15, and define a couple of things. So the first word we need to define is just, what does it mean to be an outlier in a linear model? These are just points that are out of the pattern. Or have a large residual. What about this other word we saw, which was the idea of being high leverage? These are points with very large or very small x values. So that was like the points A and B here that had these sort of extreme x values, extreme distances from x bar. We refer to those as high leverage points. And then what does it mean to be influential? Those are points that, if removed, would cause big changes. Big changes to the slope, to the y-intercept, or to R, which is the correlation coefficient. The last little takeaway here is that, in general, with horizontal outliers, like A and B, those tend to tilt the line towards them. And so we saw that really dramatic tilting with those high leverage influential points A and B. Whereas with vertical outliers, like C and D, those tend to have a less of effect on the line. I mean, we will see these shifts up and down, and we might see a small change to the y-intercept, but typically the slope stays the same. And these just don't exert the same leverage on the line as horizontal outliers tend to do. So horizontal outliers have the potential to really impact our entire model. Okay, so hopefully we have an understanding of these ideas. I want you to take a minute and try A and B, and we'll come back.